we're talking about a guarantee that can be proven for the EM algorithm, namely that the sequence of estimates produced by EM gives a non-decreasing sequence of likelihoods. And so we just drew the picture here to see why these assumptions, if these assumptions hold for the log likelihood and this Q function, why that implies this guarantee. And next we're going to formalize this. It's actually just a very simple thing, but let's write it down. So L of theta t by property 2, this is Q theta t with it Q theta t plus G theta t. And if we maximize this over the first argument, then of course it doesn't decrease. This is certainly greater or equal to that. So the max is greater or equal, and G still sticks around here. And now this max is by definition equal to Q of theta t plus 1 with theta t, because Q theta t plus 1 maximizes this as a function of theta, right? That's exactly the expression above, except it's the argmax. So this becomes Q theta t plus 1 with theta t plus G theta t. And this, thinking of this as a function of theta t plus 1, we can apply property 1. So if you put theta t in for theta naught here, and theta t plus 1 in for theta, this is less or equal to L theta t plus 1. And that's exactly what we wanted. L of theta t less or equal to L theta t plus 1. Very nice and simple. And that's exactly, if you sort of trace through these steps, they're exactly what we talked about in this intuitive sort of picture. The maximum, this inequality was going from here to here. We were maximizing this. And then this inequality was going from here to here. This was because it was an upper bound. Nice and simple. Okay, so but now we have to show that these properties do indeed hold. So let's do that. So that's step B. Let's make it a yellow step B. In step B, we need to prove these. And we're going to do it using the relative entropy. So L theta equals the log, just by definition, it's the log likelihood. And we can always introduce a sum over, I'm just going to go through this without really, there's some steps in here that are not intuitive to explain why you take them, but you'll see why as we sort of go through the computation. So that we can always do this for any PMF Q, lowercase q. It just sums to 1. And now we'll do a sort of very strange sort of thing here. That was sort of, if that wasn't strange enough, we can put some stuff in this log. So let's do it on this line here. So we'd like to get something that looks sort of like log of p of x and z. So to get that, we can multiply this by the probability of z given x under this theta. But then we need to cancel that. So let's cancel that. And then we also are going to want to introduce a q of z in here. So let's do that and cancel that also. So we're just multiplying by 1 here. You can always do that. And now let's break this apart. Let's use the property of log of the product is the sum of the logs. So this is log of p of x and z plus the sum of with this part. So we're going to take q of z log q of z over p theta z given x plus, then we have the last part, and actually it's going to be minus because this is on the bottom and I'm going to pull it up. Each of these is a sum over z, just moving the sum through. Q of z log q of z. And now if you sort of know your information theory, it may be clear to you why we sort of did that, because this you may recognize as the entropy of Q. And this you may recognize as the relative entropy, or KL divergence, as they sometimes call it, of Q with this conditional distribution. So let me write that as P dot given X to indicate the whole distribution, rather than to make it clear that it's the distribution and not a particular value. So this equals the relative entropy. And this thing is looking like something we sort of want. We want to get the log of the joint distribution here. So maybe I should mention, if q of z happens to be 0 for some z, then we get log of 0. But it's okay because we still have 0 out front, and we always interpret 0 log 0 to be 0 whenever we're working with entropies or relative entropies. And if the denominator here happens to be 0 when q of z is not, then we interpret that to be infinity. So everything is defined. Okay, and now let's choose a particular q. So let's choose because this held for any PMFQ. Let's choose q to actually be this conditional distribution, p of z given x. Because if you look here, then that's going to give us the conditional expectation of log p sub theta of x and z plus the relative entropy of that conditional distribution with itself. Oh, actually, not theta. We wanted this to be, I want to make this theta naught. I want to introduce a new theta, right, to get the conditional expectation under theta naught. So that becomes theta naught, p of the two conditional distributions, theta naught with theta. And then we have minus the entropy of that distribution, theta naught, that conditional distribution. And now, from our choice here, this is just the conditional expectation, just like we wanted. That was what we were sort of aiming for by choosing that. This is the conditional expectation of log p theta of random variables x and z, given that x equals little x, because we've got the little x here. We condition on that, and we have this. We're taking the expectation with respect to this conditional distribution. So that's just the definition of conditional expectation for a discrete random variable, discrete distribution. And this is always non-negative. Relative entropy is always non-negative. So in fact, what we have here is that this is greater or equal to this plus this other function over here. And let's just call that g of theta naught. That's just some function of theta naught. And we'll call it g of theta naught. And so this whole thing, this is greater or equal to Q, right? This was Q. This thing here was exactly, I mean, that was what we were sort of trying to build up toward. That's this Q function. It's exactly that. So this is Q of theta with theta naught plus G of theta naught. And things are looking very good now because we have that L of theta is greater or equal to Q of theta with theta naught plus G of theta naught. And that's exactly property 1. And that holds for any theta and theta naught. So things are looking good there. We've got property 1, check. And we just need to make sure that we have property 2. So property 2 says that if theta equals theta naught, then this holds with equality. So let's see what happens there. Well, the inequality came when we applied it to the relative entropy here. But it turns out that if theta equals theta naught, then what does the relative entropy do? Well, if you know relative entropy, you know that it actually equals 0 when these two distributions are equal. And in fact, it's pretty easy to see why that's the case, because if remember Q was this conditional distribution, and if theta equals theta naught, then this is just they cancel. You just get 1 here, and log of 1 is 0. So that's just 0. So this inequality becomes an equality when theta equals theta naught. And so therefore we have L of theta greater or equal to Q theta naught plus this function G of theta naught with equality when theta equals theta naught. Equality. And that's exactly what we wanted to prove. Exactly what we wanted to prove in part B to ensure that these conditions held for part A to be valid. So that proves the proposition. And the main sort of points here to remember in this, and of course, right, the proposition was that these likelihoods are increasing, and this we showed that they're non-decreasing, and we showed that this L of theta was non-decreasing, and so since log is monotone, then we have this. So the main steps in this proof, the thing to remember is this picture. That's the main idea. So if you remember this picture, and you from here to here you're non-decreasing, and here to here you're non-decreasing, that's really the main idea. So that's the thing to really get your head wrapped around. And the other main point in the picture and these sort of two properties, these sort of go along with the picture. The picture sort of helps you to remember those. And the other main point was just getting this log likelihood, sort of breaking it up to be able to use the relative entropy and the non-negativity of relative entropy, and the fact that it's equal to 0 when theta equals theta. In fact, it's equal to 0 if and only if these two distributions coincide. But we didn't need that here. But breaking this up in terms of the relative entropy was the other sort of key step in this proof. Relative entropy is a very nice general sort of tool. This is another sort of nice illustration of using the relative entropy. So that's the guarantee for EM. And I think it's a nice little proof, and I hope you enjoyed that.